Today I am going to describe the real face of the Chinese hypersonic missiles. At the moment, China deploys YJ-17, YJ-19, YJ-20 and 21 series of hypersonic missiles, ZF-21D, YJ-21 and KD-21. They are divided into three categories: anti-ship ballistic missile, ZF-21D, YJ-20, air-launched anti-ship ballistic missile, KD-21, YJ-21, hypersonic cruise missile, YJ-19, hypersonic glide vehicle, YJ-17. Let's take these categories one by one. The ZF-21D is widely recognized as the world's first operational anti-ship ballistic missile and is often referred to as the original carrier killer. It's a two-stage solid propellant missile launched from a road mobile launcher. The ZF-21D has an estimated operational range of approximately 1500 km. Its key technology is its maneuverable re-entry vehicle, which is designed to make precise adjustments during its terminal descent to strike a moving warship. The missile is believed to achieve speeds of up to Mach 10 during its final approach, presenting a significant challenge to shipboard defense. To be effective, the ZF-21D relies on a robust network of external sensors, including satellites and over-the-horizon radar, to provide initial targeting data for its re-entry vehicle. The YJ-21 and its air-launched variant, the KD-21, represent the next generation of this capability, moving the threat from land to sea and air. The YJ-20 is a ship-launched hypersonic anti-ship ballistic missile with re-entry vehicle, first seen being fired from the Type 055 destroyers in 2022. The air-launched another ballistic missile, designated KD-21, is carried by the Chinese H-6N, H-6K series long-range bombers with a single aircraft capable of carrying 4 missiles. Both versions have claimed to have range of up to 1500 km and terminal speeds approaching again Mach 10. Beyond ballistic missiles, China is actively deploying a new family of hypersonic weapons that leverage atmospheric flight for different attack profiles. The YJ-19 is reported to be China's first operational scramjet-powered hypersonic cruise missile designed for naval launch. As an air-breathing system, the YJ-19 can sustain powered maneuvering flight at hypersonic speeds within the atmosphere. This capability represents a significant technological achievement and provides a threat that flies at lower altitudes and on flatter trajectories than ballistic missiles, challenging different parts of a defender's sensor and engagement envelope. Its design for integration into standard naval vertical launch systems indicates an intent to field this capability widely across China's modern surface fleet. The YJ-17 is a hypersonic glide vehicle based on ZF-17, developed for the anti-ship role. After being launched to high altitude by a rocket booster, the YJ-17 vehicle detaches and begins an unpowered glide toward its target at speeds estimated up to Mach 8 over a range of approximately 1200 km. Its design likely incorporates wave rider principles, where the vehicle uses its own shockwave to generate lift, enhancing its maneuverability and range. The YJ-17's ability to execute sharp, unpredictable maneuvers during its glide phase is its primary advantage, designed to defeat defense systems that rely on predicting a ballistic trajectory. The YJ-17 and YJ-19 are part of a new quartet of advanced anti-ship missiles, including the YJ-15 and YJ-20, that signal a deliberate move toward a layered, multi-platform and technologically diverse maritime strike capability. Despite the impressive performance characteristics of these weapons, their reliance on hypersonic speed within the atmosphere creates a set of inherent physical constraints and vulnerabilities that can be exploited by a prepared defender. The very phenomena that make them fast also make them detectable and, in their final moments, interceptable. While the maneuverability of hypersonic weapons complicates tracking, their flight profiles make them detectable at long ranges. Ballistic missiles and HGVs must fly to very high altitudes to achieve their speeds and range. Hypersonic glide vehicle is typically glides at altitudes of 40 to 80 km, while anti-ship ballistic missiles reach even higher apogees before re-entry. Even lower flying hypersonic cruise missiles operate at altitudes of 20 to 40 km, far higher than traditional seismic cruise missiles. The range of the visual radio horizon for a glider flying at an altitude of 60 km is 1064 km, and for a hypersonic cruise missile flying at an altitude of 33 km, it is 773 km. Therefore, the defending side will have about 7 to 10 minutes to react with countermeasures. What is interesting is that if a classic subsonic anti-ship missile like the YJ-83 attacks an American destroyer, then due to the low altitude flight profile of the missile, the American ship will have only 2.3 minutes to react. The most crucial vulnerability of any object traveling at hypersonic speeds within the atmosphere is a phenomenon known as the plasma sheath. At speeds above Mach 5, the air in front of the vehicle cannot move out the way fast enough. It becomes intensely compressed and beats of thousands of degrees, causing the air molecules to ionize, that is, to be stripped of their electrons. This process creates an envelope of electrically charged gas or plasma that surrounds the vehicle. This plasma sheath has a profound effect on electromagnetic waves, including radio frequency signals. The dense plasma can absorb, reflect, or severely distort radio frequency signals, creating a communications blackout. This blackout affects signals crucial for the missile's mission, such as GPS signals needed for precise navigation and, most importantly, the signals from the missile's own onboard active radar seeker. To hit a moving warship, the missile must use this seeker in the final seconds of its flight to find the target, lock on, and guide itself to a precise impact point. If the plasma sheath is too intense, the seeker is effectively blind, unable to transmit or receive the radar waves needs to do its job. To overcome this fundamental physics problem, the missile has no choice but to slow down as it descends into the denser air of the lower atmosphere for its terminal attack. By reducing its speed, the missile reduces the friction and compression, which in turn reduce the intensity of the plasma sheath to a level where its seeker can function effectively. This necessary act of deceleration from hypersonic to high supersonic speeds creates a predictable and exploitable window of opportunity for defensive interceptors. The theoretical vulnerability of hypersonic weapons during their terminal phase has been validated under real-world combat conditions in Ukraine. Russia has employed its Kh-47M2 Kinzhal missile, an air-launched ballistic missile with a claimed top speed of Mach 10 and maneuvering capabilities, making it a close analog for systems like the Chinese DF-21D and YJ-21K-21. Contrary to initial assumptions that such weapons were unstoppable, Ukrainian Air Defense Forces operating US-supplied Patriot missile systems have successfully and repeatedly intercepted Kinzhal missiles targeting Ukrainian cities. Independent analysis of this engagement confirms that the Kinzhal, like any ballistic object re-entering the dense lower atmosphere, experiences significant deceleration due to the atmospheric drag. Its speed in the terminal phase, when it is low enough to be engaged by systems like the Patriot, is estimated to be in the range of Mach 3 to Mach 4. This speed, while still very fast, is well within the design engagement envelope of modern interceptors like the Patriot PAC-3 and European Aster-30. This combat data is crucial because it moves the discussion from theory to fact. It demonstrates that the hypersonic label, while accurate for the mid-course phase of flight, is misleading when assessing terminal defense capabilities. The defensive challenge is not to intercept a target at Mach 10, but rather to intercept a highly maneuverable target at high supersonic speeds. Western nations, led by the United States, field a number of advanced surface-to-air missile systems capable of engaging the high-speed maneuvering threats presented by Chinese ASBMs in their terminal phase. This list includes the SM-6, Patriot PAC-3 MSE, Aster-30 Block 1 and 2 missiles with MRBM and IRBM interception capability. I may get stoned, but I think even Israeli air defense systems such as Barak 8ER on Indian destroyers seem to be capable to intercept Chinese hypersonic threats. One of the primary tactics envisioned for Chinese ASBMs like the DF-21D and YJ-21 is a very steep terminal attack profile, often described as a death dive. The missile would approach its target from an angle of 80 to 90 degrees, coming almost straight down. This tactic is designed to exploit a geometric limitation in a single ship's primary air defense radar, which is optimized to scan the horizon and has a cone-shaped blind spot directly overhead. A missile entering this cone not be tracked effectively by that specific ship in its final critical moments. During the Ukrainian conflict, the Russian Iskander missile could have hit Patriot air defense launchers with this approach, since the angle of attack exceeded 80 degrees of the Patriot radar vertical field of view. The direct counter to this tactic is the US Navy's cooperative engagement capability. The CEC is not a weapon but a high-speed, high-fidelity sensor networking system that fundamentally changed how a naval battlegroup defends itself. It links the individual radar systems of every ship and specific aircraft in the group into a single integrated air defense network. The power of this system lies in its ability to decouple the sensor from the shooter. The Chinese deep dive tactic is predicated on defeating a single, isolated ship. However, US carrier strike groups operates as an integrated network system with cooperative engagement capability. If the target missile enters the radar blind zone of Ship A, it remains clearly visual to the radar of Ship B, several kilometers away, or even more effectively to the high-altitude lockdown radar of an E-2D Hawkeye flying overhead. Through the CDC network, the precise tracking data from Ship B or the Hawkeye is instantly and continuously available to Ship A. This enables a capability known as Engage on Remote, where Ship A can launch an SM-6 interceptor and guide it to their target using the high-quality tracking data provided by another platform in the network, even if its own radar cannot see the threat. CEC effectively eliminates the individual ship's blind zone by creating a single distributed ground sensor that sees from all angles simultaneously. This transforms the defensive problem from a series of one-on-one duels into a collective many-on-one engagement, directly neutralizing the core tactical premise of the ASBM's steep terminal dive. So let's make some summaries. The challenge posed by China's hypersonic anti-ship missiles is real and demands sustained focus and investment in countermeasures. This includes continued development of space-based sensing for persistent tracking, the proliferation of networked warfare capabilities like CEC across the fleet, and the procurement of advanced interceptors like the SM-6 Block 1B and PAC-3 MSE. However, the hype surrounding these weapons as unstoppable threats is not supported by a pragmatic technical and operational analysis. Their vulnerabilities are as significant as their capabilities. The threat is asymmetric and serious, but with the right technology, doctrine, and continued investment, it is a manageable one. So that's all. If you like this video, please subscribe and share. Next time to see you. Goodbye.